Okay, so welcome back everyone to the second part of the session, which is going to be, well, it's called image correction for reflectron and straight flight path instruments. So essentially what we're going to look at now is how does a reconstruction for a real atom probe differ from the reconstruction of this idealized system. And since we had all these issues in the first session, I'm just going to repeat the stuff from the first session quickly as well, hopefully to clarify anything that is not that has not properly been understood. And Martin would actually send out the data that I originally had planned for the first session, which is actually straight flight path instrument reconstruction from some old data from Sydney, which also is a relatively small data set. So maybe you can work a little bit easier with that. And so let's start again with the sketch of the field evaporation. So now I've just taken the image of an actual sample that I had before and just put it into a sketch with the base geometry. And use that one. With the base geometry that we're having, and looking at what happens if you have an actual real atom probe. If you don't have an idealized system, but you have some kind of electrostatics in there, which might be a reflectron, which might be a detector that's not at ground potential, which is the case for almost all atom probes. Okay, so the sketch that I've made before was just one of, you have a specimen, and all that you have in your system is a detector that sits at some distance away from your specimen. Obviously, this is not to scale because I cannot draw at nanometers. And your specimen has some kind of top radius that you may or may not know. Radius evolution we've discussed already a little bit. And if you look at the actual flight path of an ion, so let's say we have an ion that, why is it? Oh, I'm drawing on the wrong plane. Let's say the ion originates somewhere here. So we've got an ion here that wants to leave the surface. So what's going to happen is that originally the ion's going to go out, some radial direction here, but our detector here, our detector is not at ground potential. Our detector is at, sorry, I should start with the specimen itself. But if you look at the field lines around the specimen, then I can just sketch them vaguely. Because you have a shank, essentially the electric field is going to push the originally radially leaving atom, not just in a purely radial path, but the path is also going to be a little bit inwards curved. It's going to come back to the optical axis a little bit. And on top of that, the detector, so the shank of the sample is going to repel your atom. If you've got a very wide shank, obviously that's going to be more, that's going to be a stronger effect than if you've just got a very narrow shank. On top of that, the detector, if you've got a straight flight path instrument, oh sorry, that was a sketch for ground, we're not going to ground yet. The detector is also for technical reasons probably going to be at some potential of 2 to 3 kilovolts. Kilovolts negatively. So it's going to attract your atom. It's going to attract your ion. So your ion is going to fly in a bit of a curve. And this is what we call image compression. Because it's a compression. It's a compression relative to the ion going straight out. So we have an angle theta uncompressed, and we have an angle theta compressed. And our image compression factor is the ratio between theta compressed and theta uncompressed. Between theta compressed and theta uncompressed. And it's sort of an approximation of this, this curve that the atom's flying. It is, you need to know the electrostatics of your instrument in order to be able to actually simulate that. But that is our approximation that we're making. This is why we're having the image compression factor. The field factor you already know is our fudging factor to get from the voltage, because we know that our radius, color, because we know that our rate, we have two greens, that our radius equals voltage divided by, or can be approximated by voltage divided by this fudging factor K times the evaporation field, which we may or may not know very accurately. And this essentially gives us the approximation for the trajectory. And from this image compression factor, you can also calculate what this distance is here. So there's just one subtlety. If you look in that corner up here, if I can just, maybe I can just zoom in. If I can just zoom into that corner here. So if you're doing your reconstruction, and we originally just moved our atom back to here. Maybe I'll use a different color for this now. Originally we just moved our atom here. In the olden days of non-wide angle atom probes, all you did for the Z correction was actually put your atom right here. This is not actually correct for any angle that's further apart from here, further out here. If you had an old atom probe and you might just cover the bit from here to here, then that's not actually a bad approximation. But on a modern atom probe, we actually put the atom following that vector here. And this is the difference between a wide angle reconstruction and a small angle reconstruction. But this is essentially our why can it not jump to the original size? That is weird. Anyway, doesn't matter all that much. So this is the difference between a wide angle and a small angle reconstruction. But what actually does happen during the reconstruction is that this image compression factor will actually change, simply because this is a fixed potential, but our sample, the potential our sample is at, which is our positive with respect to ground, our VDC. We might have an electrode with a pulse voltage on top of that. So the ratio between VDC and the detector voltage changes. And so the image compression changes during the experiment. And what we are going to do is look at how we can correct that. So this is the first thing that we're going to do. And the second thing we're going to do is looking at reflectrons. So if you have a reflectron, then the reflectron will distort the image of your sample. And what we've done to quantify that is just put a grid that we've made in front of the microelectrode. Because then you can actually see what the local distortions are. This is the magic I was talking about. Earlier. So we just have written a simple algorithm where we put this grid in, then we extract the grid nodes. That's why it was called intersections, the data that I loaded in before. And then what we do is create a mesh from that, and that transform that mesh into the shape that we know it has. But I'm going to explain it in a little bit more detail when we get to the reconstruction using reflectrons. But for now, we're going to look at reconstructions using straight flight path instruments. And now we should actually have now I hope you all have the data to do that. So let me just clear out all the data that I have in my workspace. And now I will start copying all of the code that I'm using into the chat window, so that all of you can just run the code. Okay, so let's jump right into it, and we're going to use the reconstruction file, the reconstruction workflow I've given you before. So let's just start with the first step, which is loading the data. And in my case, it should now be in the test data, simple grain boundary. No, Martin, where have you put the data? No?
I did not move it. Should be still in the same folder.
Okay. So
X and Winterschool test.
yeah.
No, Winterschool data something.
But you've sent it out to everyone.
This is correct.
This is great. So this is a grain boundary in the superalloy. So we can load that in. It's a relatively small file. And we can also load in the accompanying range data. Yeah. And with just with this few lines of code, you can just automatically connect or load in the mass spectrum as a reference variable. Okay, so we have a small data set from A718, contains like half the periodic table. And then we are just going to allocate the atomic identities or ionic identities to each of the hits. So you can now scroll through again. We can see which atom is identified as what. Of course, if you have ambiguous peaks, then this identification may or may not be all that great. And we have the ion volume now allocated. And can go and in this case don't do any reconstruction trickery, so don't do any corrections, but we'll jump into the corrections in a second. And set up the reconstruction. In this case, the detector is not 5 millimeters in diameter, but rather in this case it's 78 millimeters. So this is the diameter of the so if you buy the Hamamatsu microchannel plates, the funnel ones, you can only get up to 80 millimeters, but 80 millimeters is sort of large but standard. And so the older chemical atom probes used to use the 78, 80 millimeter detectors, and the new ones have to use them more or less because it's the largest funnel MCPs that you get, at least the straight flight path ones. With the reflectron ones, you have smaller ones. In this case, the detector efficiency then would be 0.55 roughly. Of course, there are ways to calibrate that. The flight path length is 90 millimeters. And image compression factor, I don't know. We kind of have to guess that, right? So we don't really know. Anyway, I set it to 1.2 for a reason before, and I'll explain that. When we get to the reflectron calibrations. Okay, so we can run that section. And and calculate. So the evaporation field is probably about 35 because it's a nickel-based material, and we're just going to use the voltage for the radius evolution. And then I'm not going to do a reconstruction including a dataset hull because we haven't gone to that yet, but rather I'll do it the way I had it here. And let me just copy that into the chat. And with that, we're supposed to have our reconstruction. So I can have a look and in this case go and, I don't know. I know there's some boron segregation, so maybe boron is a better species to visualize in this case. And now we have our little grain boundary. And let me just copy that in. Let me just copy that in for you. And yeah, we've got a pretty nice reconstruction. The only thing we can see in this reconstruction is, yeah, maybe our grain boundary is a little bit more bent than it should be. And we're gonna get into how actually to systematically work on that in one of the afternoon sessions. But for now, probably the sample was maybe a little bit sharper than what we see here. So maybe our radius is actually a little bit sharper. So we can go and maybe do it that way. Maybe change the field factor. No, that made it worse. Yeah, that was thought the first one around. Yes, you are supposed to have that. Martin, have you sent out the file? Is there?
I'm sorry. I just included, and I only included the EPOS, but now I'm about to zip everything up, so you will get also the mass spectra. Yeah, sorry for this.
Okay. So maybe I'll just jump into the explanation of the image decompression before. So I don't have too many. I have data to show it to you, to show that image decompression to you. So okay, so we're in the middle of explaining why you would need an image decompression. So essentially that changes, and there's actually papers out there that have discussed that already a while ago. And the first one that explicitly discussed it was a paper by Baptiste, and it's called Dynamic Reconstruction. I don't know why he chose Dynamic Reconstruction, because there's actually nothing dynamic about it. So there's no dynamic would mean time dependent, which it's not. But what they have already found out is that if you look at, for example, the crystallographic poles in field desorption maps, what would happen during the experiment is that they would, their positions would change. Essentially, the image compression would decrease as the evaporation voltage goes up. And they did that actually using crystallographic poles, and then come up with some nice curve of how to correct that. I did that a little bit differently, but let me just show you the nice videos for that, how that actually looks like. So this is actually a field desorption map movie from an aluminium specimen, and what you can see is that the image actually gets larger as the evaporation voltage goes up, as the evaporation progresses. So this is an aluminium data set. Why? And this is a data set from silicon. You can additionally see some drift. And the question is now, how can we quantify that, and how can we actually correct for that? And maybe is it worth to correct for that? No, maybe it's not even that important to do that. But I've looked in it a little bit deeper, and you can actually improve the resolution.
Sorry to disturb you, Peter. We didn't see any video.
Oh, okay. Sorry, that was my fault. I didn't jump back to here. Okay, so let me just jump back to the movie. Yeah. So you have so which one? That was the. Yeah. So this is actually an aluminium specimen evaporating, and what you can see is that the image. So in this case, this is done on a leap. Yeah. And we did not fully fill the detector. Yeah. And the reason for that is that if I don't fully fill the detector, I can also just track the rim of the detector essentially. Yeah? And I can just look at, okay, how much does my image grow over the experiment? You can see in the beginning of the experiment, it expands quite a lot. And then it sort of doesn't grow all that much anymore. So this is some aluminium. And just as a second data set to show, this is silicon, one of the silicon pre-sharpened posts. And you can see that the image sort of at the beginning it actually expands quite a lot, and then it slowly expands a bit more and more. And the reason for that is exactly what I've just drawn earlier on the whiteboard. It's the fact that the detector is at a finite potential, 2 to 3 kilovolts. So the technical reason I've already talked about yesterday, which is usually you will want the back potential to be at ground, and we also like a little bit of image compression because it gives us more data. Here in Erlangen, we have one atom probe that's actually an electron spectrometer, where our friends over at physics have gone to great lengths to shield any electrostatics from the internal of the chamber. And the reason is because usually they have like very low energy electrons flying around in there that they don't want disturbed. And in this case, you don't have any of these effects. Yeah, they are essentially the imaging stays relatively constant throughout the experiment. Of course, we haven't done very large experiments in there yet, so I don't know if the change in the shank environment would do maybe something, but certainly the detector doesn't do anything in this case. And this is something we can. It would be nice to correct for if you do straight flight path atom probe tomography. And you can see, especially if you work at relatively low voltages, say below 5-6 kV, then that's actually fairly important. The good thing about that is that it's for a type of machine, it's actually a fairly constant change. So you'll find that graph in one of my old papers from 2016, where I've done the experiment with a couple of different specimens in 2 different instruments, LEAP 3000, LEAP 4000. Will probably be different if you've got a LEAP 5000. There's no straight flight path LEAP 6000, so I don't know how it's going to work there. But with the LEAP 3000, 4000, 5000, you can come up with a curve like that just by tracking, just by underfilling your detector and just tracking how the image changes. And then you'll see the relative detector area change. And then I've just related it arbitrarily to 6 kV. You know, I could have related it to 4 kV, but just at 6 kV, all of the data sets had some data. And then you can produce sort of a master curve. Yeah? And you can use that master curve to decompress your image. And you'll see this is done on some tungsten, and you can see some additional details on longer tungsten data sets. Of course, you know, if your data set only goes from 6 kV to 8 kV, the change is not all that dramatic, so maybe it doesn't pay off all that much. But if it goes from 3 kV maybe to 8 kV, then it's a good idea to think about doing doing that correction. Yeah. And in order to do that, we actually have I actually put for LEAP 3000 and 4000, I put the image compression matrix in. Yeah. So if you now straight flight path corrections. So here you just get a table that shows you, okay, at a certain voltage, what is the relative area of the detector relative to 6 kV. Arbitrarily at 6 kV, or at close to 6 kV, it's 1. Yeah. And you can see that, this is an extrapolation, so I didn't do measurements at 1 kV. This is actually extrapolated, but it's sort of a fit from 1 kV to 15 kV. If you want to have that very accurate, it would be a good idea to do the experiment on your own atom probe, which is not particularly hard. All you need to do is maybe take one of those pre-sharpened posts, underfill a detector, and then just let it run, well, until it stops. You don't even need pulsing. You can just switch off pulsing your laser, no voltage pulsing. All you need is field evaporation, and then you can produce. You can calculate what area each at each voltage a detector fills, and I'll show you I'll show you later today how to do that. It's actually not particularly hard. I could actually show you straight away, and then create your own calibration curve. I can just make a small plot so you can see what this looks like. Well, that's not the X, that's the Y value. I want to plot that versus voltage. So this is essentially the calibration curve that we have here. And you can see below 5 kV, this is the change. The change is actually fairly significant. Okay, so how do I do the decompression then? It's relatively simple. All you have to do is divide your x and y detector coordinates by the linear compression factor. That's essentially all you have to do. So there's something called a V model. You need to do an interpolation from that. But it's a relatively straightforward thing to do. And if you want to have the individual areas, you can actually use a Detector Hull algorithm, which will give you the area the effective detector area for each slice of detector stack that we're going to get into later. Okay, so this was the straight flight path correction. And Martin sent the data out, so we're back in business with the reconstruction data, and we can jump back into the reconstruction. Okay, so okay, so do at least some of you have a working reconstruction from that data? I see one green tick. So from here on, all you have to do is play with the reconstruction parameters, or maybe come up with some smart way to automatically determine, what would, for example, give you a flat grain boundary, something like that. And we're going to do that later today. We're going to do that later today, and I'm going to show you how to use objects in your data to do a good estimation of reconstruction parameters. Okay. Anyone else? Just one person with a reconstruction. Two. Okay, so then let's jump into the whole business of doing reconstructions for reflector instruments. And we have already done one earlier, because now with this reconstruction, all of the reconstruction parameters we used physically made sense. Yeah, so we used a flight path length of 90 millimeters, which is physically the flight path length of the instrument. Yeah? We use a detector efficiency of 0.55, which is kind of, the plates have 0.6 open area ratio, and then you get a 90% conversion efficiency. But, depending on, if you have massively multiple event hits, maybe that's not as correct. Yeah. For the detector area, we just took from the whole detector. Yeah. So it's 78 millimeters. Or 80 millimeters, I guess, if you do proper reconstruction, a self-consistent reconstruction where you check with external sizes, then any error you make in the detector area will actually sort of being compensated by offsetting the field factor and the image compression factor. Yeah. Okay, so let's get into the reflectron business now. So how many of you have reflectron atom probes? Or working using reflectron atom probes? Probably the majority, right? I think everyone just started falling asleep. So, what does the whole situation look like in a reflectron atom probe? So, where did my pen go? Oh, there you go. So if you've got a reflectron atom probe, and we do have one here in Erlangen as well, what happens is you've got your sample somewhere here, yeah, and just like we talked about yesterday, then you have some kind of electrostatic bucket, yeah, and then you have a detector here. And there's actually a lot of knowledge that goes into designing that bucket, yeah? And there have been various iterations over the years to make them better and better. Essentially they work by having an internal electrostatic field. Yeah, that's a very defined field. You have an entry mesh and you have an exit mesh. Yeah? And some of the ions will crash into that mesh, and that's why our detector efficiency with the reflectron is a bit lower than with a straight flight path instrument. But you get very good time focusing. What you also get is you get an image distortion. And I've showed the image distortion yesterday already. And so we can't really use the raw detector coordinates for a good reconstruction, because we will have those distortions. But what we can do is we can sort of create so this is our detector. But what we can do is we can put an object of known geometry here. Yeah? In our case, a grid. Yeah? And then we'll get an image of that grid on the detector. And that grid contains all of the imaging properties, information about the imaging properties of the reflectron. Yeah? Because obviously that's Kamika's thing. We don't want to have to bother them about all the IP and everything. Yeah? So all that interests us really is what happens at our sample, and essentially how can we go back to the situation, to this situation here where we just have a sample, the counter electrode and a detector. Yeah? In this case, it's just a virtual detector plane. Yeah? So where we have everything that's sort of related to the sample, which interests us as the users, yeah, is happening here, and everything that's happening that's specific to the. Here we've got the reflectron, and everything that's specific to the imaging of the reflectron happens here. Yeah? And all we need to do is have some function that makes our virtual detector coordinates. Let's call them d virtual as a vector, because they have the x and the y, is some kind of function of the detector raw coordinates. And the question is, how do we come up with that function? And the way we came up with that function, obviously it's not like a nice analytical expression or anything. It's just putting a grid here and then approximating it. Kamika calls it a launch angle map. It's built into IVAS and AP suite. I don't think you have access to that. But yeah, it's not really necessary. We don't have to bother them, and we'll just do our own thing. In practice, how did that work? So in practice, it's we just created that grid, put it at the behind the local electrode. So if you look at the local electrode, so the local electrode, this is about 5.5 millimeters. I haven't determined it to the last digit of precision, so it might be 5, it might be 6, but there or thereabouts. It's about that. And the diameter then is about 5 millimeter as well, at least for our atom probe. I showed you yesterday that the images look quite different for a LEAP 4000 and for a LEAP 5000. We don't have a LEAP 3000 reference data set yet. We'll have one soon. And maybe at some point one of you buys a LEAP 6000 and wants to do that calibration as well, then you can just let us know. And the process is then relatively easy. You just collect some data. Then you outline essentially in the end what we want to know is where those intersections are. So we have an algorithm that can outline the intersections and then create a mesh. And then just here we've got this transformation. This is our function, and this is our function where this is, what did I call it before? dv. So this is our d virtual, and this is our d raw. And the good thing about that is that's actually something that's unique for one particular system. So you don't have to worry about all of that, what's happening. All you need is the calibration file. And as I said, we currently have one for a LEAP 4000 XHR, because that's what we have. And we also have some data to do that for a LEAP 5000. The guys in Oxford were so nice to do a measurement for us. And maybe we'll have one for LEAP 3000 pretty soon, and for LEAP 6000 as well. And this is the reason why we had so weird reconstruction parameters earlier. But let's now then jump into a fully fledged reconstruction using all of the good stuff that we have. So the question in the chat is, how can I solve the MATLAB error that unrecognized function or variable flight path length? Well, you need to assign a value to flight path length. The variable just doesn't exist in your MATLAB session. So you just, you just create the variable. So you create flight path length, and you just say, whatever the flight path length is. For the data earlier, it was 90 millimeters. And then you have the variable. How do you run the reconstruction setup section? Yeah, you have to define a flight path length. You have to know what the flight path length is for your instrument. And the reason is that for every instrument, this is going to be different. So as I said, as I explained right now, for our virtual detector in the Reflectron atom probe, we have a virtual flight path length that is very short. But if you have a LEAP 4000 or 3000 SI, you can change the you can change the flight path length. Yeah, you can run it at 90 millimeters, you can run it at 110 millimeters. Yeah, you can actually change that length. I don't think the newer ones can do that anymore. Wasn't that useful in the end anyway. But I think in the old ones, I don't know what the range was. I think Rob would probably know. I think it was 90 to 110 or 90 to 125. Anyway, there was a range, so you could move the detector. It's a cool feature, but I don't think it was used very much. So eventually, I think they got rid of it. Okay, yeah. So you need to define the flight path length. Okay, so let's start from scratch again, and now we're going to do a reconstruction for an ugly data set. Yeah, we're going to dive right into the deep end. Yeah? And so I'm going to clear out all the variables, and I'm going to start from scratch, and I'm going to put all of the different commands that I'm going to use into the chat, so all of you can follow. Okay. Okay. So another question was, how do you run the reconstruction setup section? So if you have a MATLAB script, so Martina usually puts like run buttons in there. But if you go Control Enter, that also runs the individual section. So I just press Control Enter, and then it will run one section. But I will actually do it in the. Should I do it in the? I will do it in the live script. Okay, so let's just load everything in again. And the data set that I'm using now is also one that you have, which is called laser tracking issues, or which is in the folder laser tracking issues.
Sorry, Peter, I think you're on the wrong screen. Or at least we can't see your MATLAB.
Thanks for the hint. Okay, so I'll start from scratch again, and we're using the one called laser tracking issues. Because this is already a very good motivator why you want to do your own reconstruction in this case. Yeah? And I was wrong. Laser tracking issues. Load that EPOS file. That's a relatively large one. Yeah? So you get a bit of a feel of how long it takes to reconstruct relatively large data sets. And actually, it shouldn't take all that long. So the largest data sets, maybe 100 million atoms, shouldn't take more than a second or two. By the way, if you have a okay, thank you. So if you have a good and large GPU on your system, on your computer, you can actually move all of the data over to the GPU and do everything on the GPU as well, which makes the reconstruction extremely fast. Yeah. By the way, the reconstruction that I'm showing you here is not actually optimized. Most of the time during the reconstruction is spent accumulating the volume of the atoms, yeah? Creating the cumulative sum, because they cannot be parallelized easily. Yeah? And so if you create a cumulative sum of the volumes beforehand, you can also speed it up significantly. Yeah? So you can do 10 reconstructions a second. On the GPU, 100, 1,000 reconstructions per second, and then just look up which one is the best one. Okay, so we've got it loaded in now, and you can see here we've got a POS file with about 33 million atoms, 34 million atoms. So this is a sizable atom probe data set. And we're going to load in the ranges for that. Again, just press Control Enter, then it will run the section. APT school data. No, which one was that? APT school data. No, Winterschool. Test data, laser tracking issues, range figure, and it already has created. It has created a variable, that's linked to the area plot, which represents the mass spectrum. By the way, if you want to do that on your own data and you have RNG files, we have a workflow called workflow load RNG file, which is just a workflow that imports everything from an RNG file into your ranges, including the color scheme and everything, so they can keep working with all of your good Kameka stuff over there. Okay, so we've got the ranges loaded in. And the next thing we're going to do is we are going to allocate our atoms to the individual ranges. And we are going to calculate the ion volumes from the atomic volumes, just like I showed you before. Again, may or may not be a good idea. You know, sometimes you have a better idea of what the individual volumes of your atoms are than just taking them from elemental volumes. And we've heard some arguments for that earlier already. Yeah. So you have a crystal where the elemental volumes, and oxide where the elemental volumes are not a particularly good approximation of what the volumes of the atoms are in your final reconstruction. Yeah. Okay, so now if we go into our POS file, we've got all of the columns that we need there. We've got the ion volume, and it should actually say the unit there as well. There should be a properties units. Where are the units? Okay. I will make sure that in the future we'll have the units in there as well, because usually we have the units. So if you look here, you will see that the units are millimeters. Units are millimeters. And probably we could also add some descriptions. I think this would be very helpful. By the way, if you have got suggestions for the toolbox, just mail us. We will also put up a bug tracker and a feature wishlist tracker so that we can get on top of what you guys out there would like to see. Okay, so we've moved into that. And the next thing is just we're doing our image transform. And again, this is something you usually run once on your data and then you just save it out and that's it. So essentially you collect your data, you go through IVAS and create an EPOS file, and then you just let it run through the image transform, and then it's ready for reconstruction. And that always takes a second or two. We already had that earlier today because the image transform is a computationally quite intensive task in this case. Any questions so far? Is everybody able to follow? I mean, now we haven't done anything very complicated. Actually, with the new version of MATLAB, we are finally getting asynchronous multi-threaded execution. So a lot of that stuff is going to be a lot faster in the future because we're going to be able to do a lot more stuff in parallel. It was long overdue, but we're finally getting it.
Peter,
Yep.
you actually have one of the big data sets with over 30 million atoms. Maybe we just crop it a little bit.
You can crop it if you want to. Yeah, that would make it, but now it's running already. And once we've done that, the rest should actually go relatively smoothly. But of course, what Martina was talking about is, for the demo, we might not need the entire data set, so you could just go and say, yeah, I just want to have the first 10 million counts, or the first 5 million counts, or the first 15, or whatever. And then it would obviously go a little bit faster. But I guess we've got a minute or two, and we can just wait for the image transform to finish. By the way, the image transform, if you look into the actual function, it's just written in a way that's supposed to be very readable. Just simply because the performance is not as much as an issue if you only need to do it once. But there would definitely be the potential to make it a lot faster if need be. Okay, now I'm getting impatient as well. No, just kidding. It is going to finish. It will just take a couple of seconds. But maybe then I'll just explain what we're going to do next. This is actually the data set that I'm showing you. So what we're going to do next is we are going to create a detector hull. So let me just explain to you what a detector hull is. So essentially, when we're working with reconstructions, we have two spaces. We have a detector space. We have a detector space. And the detector space has coordinates that are usually we draw them the other way around. That are x detector, y detector, and n. So essentially, it's kind of like stacking all of the detector hits on top of each other. Stacking all the detector hits on top of each other. And we transform that. So this is detector space. And we have reconstruction space. And the reconstruction space means we have x, y, and z in normal Cartesian coordinates, and then what we had before just looks like the atom probe reconstructions that you're used to. And the question for us very often is, well, where does the whole atom probe reconstruction start, and where does it end? And inherently, it's a set of points. It's a set of points somewhere in space, either in 2D space or in 3D space. And a set of points doesn't actually have a boundary. There is no one way to say, okay, this is the boundary of a set of points. Instead, what we usually do is to have some approximation for that. And let me just get rid of that. And so essentially, if you have a set of points, so what is the boundary of points? What is the boundary of points? And the one actually unique boundary that it can have is a so-called convex hull. Convex hull means you're fitting the last one was maybe not a good fit. But that's the set of lines in 2D that are uniquely separating a space with no points with a space with points. Obviously, if you have a set of points like this, that's a pretty good approximation, and I don't think anyone will argue, that the domain will look much different than that. But what if we have a set of points that looks like this? Then maybe we would argue that the domain is more like something like this, Yeah. And so what we do is we replace that this is a convex hull. We replace those lines essentially with circles, yeah? With circles of a certain radius r. Yeah? And if we have the sum of circles, the boundary points that are bordered by those circles, sorry, they should all be the same radius, obviously, we get something called an alpha hull. Yeah? Comes out of protein folding, by the way. Yeah? And this is a much better solution for something that looks like an atom probe dataset. Yeah? Because if you've got an atom probe dataset, usually the atom probe dataset is not convex. It's not convex. It has a concavity at the bottom. The problem with that is if you create a mesh from that, it's going to be very irregular because it's kind of arbitrary because of limited density and because of limited detector efficiency. It's kind of sometimes you get 3 points that are making up a boundary that are very close to each other, and sometimes they're very far apart from each other. And so that's very often not a particularly good approximation. And I'll just show you what I mean. We've cut something called an alpha hull in there as well as an algorithm. So our program is finished already, so I can go and calculate the hull. And we have that as patch create sampled alpha hull. So for your POS file, with this radius being in this case 10 nanometers.
Sorry, Peter, we can't see your MATLAB screen.
Thank you again for the hint. Yeah. So we have the function patch create sampled alpha hull, where for your POS file with a radius of 10 nanometers, you arbitrarily take 10 to the 5 atoms out of the entire set of atoms, just so that you don't take too long to calculate. But also then sometimes you get some very small triangles, and you can calculate that hull, which will give you the volume of the data set. And this is just the reconstruction as we had it, and give you the outline of the data set. But if we look very closely into the mesh, it's not a particularly pretty mesh. Yeah? So you have a lot of large triangles, small triangles. The corners are more or less well defined, but you can just try out that function. I'll just copy it in, and you can have a look into the details of what that looks like. Of course, you can increase the number of atoms that contribute. Yeah, but yeah, it doesn't really make the mesh any prettier. Anyway, you can try yourself. You can try that out. Yeah. And so what we do is actually we create a hull in detector space, where it's much easier to do. Yeah? Because in detector space, what we can do is actually that's in one of the papers that I just had open earlier. Maybe that's a little bit better than me just drawing it. Anyway, so this is just this figure. So this is what an alpha hull would look like, with a slightly ugly mesh. And what you can do with if you have the raw data, is just to outline your data, yeah, and create a hull from that. Just build it up in detector space, and that's what we're going to be doing now. You don't actually have to do much in this case. Yeah, you just have to watch the algorithm do its thing. Yeah? And then we co-reconstruct that hull. Yeah? And this is a very important concept that we're going to use a lot in the afternoon when we're doing object-based calibrations. Yeah? So we're going to co-reconstruct that hull. Yeah? And this here is actually an example of an underfill detector, which is also has some contamination on the counter electrode. So you can see that the detector isn't fully filled and so on and so forth. So we applied an additional filter, and that's actually part of the whole algorithm. Yeah. So we can go into here. Maybe I'll should I do that in? Yeah. So in order to calculate that, we're actually going to need some input. Yeah, and the input is so for this algorithm here, yeah, the question is our detector overfilled or underfilled? Yeah? If our detector is fully filled and we have a nice circular detector image, then we don't have to worry much about pre-filtering. Yeah? But if we have an underfilled detector, or we have a detector image that is not like fully circular, then we need to think about pre-filtering. Yeah? So let me just I'll just draw that. I think that's the easiest way to explain it. So just imagine you have your detector image just like you saw it before, yeah, and you have a bunch of hits on the detector image, and it forms, I don't know, maybe some weird shape like this, while the overall detector might be this large. So we've brutally underfilled our detector in this case. Yeah. So the question is, how do we outline that? And we do it with the same algorithm. We do it with an alpha hull. Yeah. We do it with an alpha hull. But the problem with the alpha hull in this case is we're always going to have some spurious hits on the detector outside our actual data area. And the reason for that is that that there are cosmic rays and radioactive decay in the detector and so on. Yeah. So we're going to have hits outside of the actual data area that we have. And so what we have implemented, or what I've implemented, is a filter that just filters those out. So it essentially just says, okay, this area is closer to this hit than to any other hit. Yeah. And because this area is very large, we're going to throw that hit out. Yeah. And then we are going to draw our alpha hull. Yeah? Once we've thrown out all of those hits that have those large areas around them where there are no other hits. Yeah? That's called a Voronoi filter. Yeah? And that Voronoi filter gets rid of the noise. If you let that Voronoi filter run on a very large data set, it takes a little while, okay? So go grab a drink, go for lunch. Yeah? This is why we're not going to run it now. But if your detector is nicely filled, like in this case, you don't have to run it anyway because you don't have any hits outside of your actual data area. Yeah. Here we also have an alpha radius, and the alpha radius has the same meaning as before. You know, if we make our detector outline, what is the maximum concavity we're allowing? The next question is, you know, if we do that via segments, yeah, if we do that for each segment of the detector, for each x thousand, x million hits, how many per segment do we want? And I've set it to about 1 million per segment, which is reasonable. You know, you can set it to more than 1 million, less than 1 million. You have to try that out. But 1 million is usually a pretty okay number. And that gives you the number of segments that you're going to have in the end. And what we're also doing is some nice remeshing. Yeah. So our 2D alpha hull is just like our 3D alpha hull is going to be something where the individual line segments are going to be very arbitrary. Yeah? So what we are doing is actually dividing it up into regularly spaced segments, yeah? Into a regularly spaced n-gon, and I've set it to this n-gon. Yeah? So these lines here on the side to be 32 lines for each segment. Now you can set it to 64, so you can set it to 16. But 32 sort of gives you a pretty good outline, usually. If you have some concavity in there, you might need to crank that up. Then we have a cap at bottom and top, and that cap has a certain number of edge loops. And I've set that to 4. Depending on whether you want to do something with those edge loops or not, you might set it to a higher or lower number. And the Voronoi filter, again, in this case, I've switched it off. If you switch it on, you need to supply it with a Voronoi noise limit. Yeah? So the question is then, which atoms should it throw out? And in this case, it throws out, it makes a histogram. It makes a histogram of the Voronoi cell sizes. Here it would be a very small one. And it just makes a histogram of frequency versus cell area in this case, not volume. And then it gets some kind of histogram, whatever that looks like, and it says, okay, here we've got the bottom 5%, and I'm going to take out the bottom 5%, which is going to hopefully be all of the hits out here, but probably also some in here, which doesn't matter because our alpha hull still will give us the correct result if we take some of the atoms in here out. That may be because they're close to a pole, they may have a small area around them, or for whatever other reason. And this just creates the detector hull. It is doing its thing, hopefully. Yeah. So you can, oh, it just plotted it somewhere else. And then it just calculates the hull for our data set for 34 segments, because we've got roughly 34 million atoms in there. Was everybody able to follow along so far in this session? I know in the last session maybe it was a bit more convoluted. I hear no no's, but I also hear no yeses. So either we've lost everyone, or everyone's okay. We've definitely lost one person.
Yeah, Peter, I have an error here when trying to run the section. It's unrecognized function. I put it in the chat. It's the alpha vol function or variable.
So this should be in the utilities somewhere. Yeah. So if it has an unrecognized function, make sure that the utilities are all on a MATLAB path. Okay, and now we've got our hull for our detector. Yeah. And this is actually something we can import, export, do funky stuff with it. The only thing, if you want to visualize it, is remember, we have X and Y coordinates. In this case, on our virtual detector coordinates, so relatively small, but 5 millimeter diameter. And the Z coordinate is its number of hits, so 10 to the 7. So if you want to display that in a 3D program, it's going to be a very, 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 very long cylinder. Okay, so now with this data set, the reason why I picked this data set for reconstruction is actually let's plot the VDC. Let's plot post.vdc. So this is a laser data set, and what we very often see with laser data sets is that, okay, now I've plotted it into some other figure. Sorry, I'll just open a new figure. So here, for example, we have the issue that we have a lot of laser tracking errors back here. So in this case, it's probably really better idea to do the approximations, or to do some fit like we had it before. So create a sample. So we have some sample indices, and we're gonna take maybe more than 1,000. Maybe we'll take 10,000. 10,000 sample points, and And we're going to go into a curve fitting session again. And our X data is sample index and our Y data is sample VDC. And sample index, Y data, sample VDC. And now we have a nice function here as well. And let's see if we can use a polynomial. Maybe we can, maybe we can't, who knows. Yeah, so probably a polynomial isn't a particularly good approximation here. I don't remember what I actually used. Did I use I think I used a smoothing spline. And I think 10,000 points is already a lot for MATLAB to fit in a relatively short amount of time. So maybe maybe I'm gonna do fewer points than that. No, so maybe we'll stick to the 1,000 points that we had before. And do some crazy polynomial. No, that's probably not a good idea. Maybe it's a better idea to have a smoothing spline. That smoothing spline in this case is then probably a pretty good approximation apart from the very, very earliest hits here. Here it's probably not a particularly good approximation. But anywhere beyond that, it looks kind of definitely better than what we had before. And then again, I'm just gonna save the fit to the workspace. And we only need the model, so we'll call it VDC model. Okay. And I'm just going to leave that open for now. And now the radius is then our VDC model of pulse dot ion index. And evaporation field, I think that's also a superalloy, so yeah, I think what we had before with evaporation fields and so on was actually fairly okay. Okay, so now we can have a look at what our radius approximation looks like. So I'll just open a new figure and plot the radius again. Put the radius again. And now if we plot the radius, it's not perfect, but it's definitely better than what we had before with wherever that plot ended up. Yeah, it's probably better than what we had before. So this is just a voltage plot with all those laser tracking issues, and here we've gotten rid of those laser tracking issues and have a better idea of what the radius evolution is of our specimen. In this case, of course, it's radius, so you might still just adjust it to fit maybe the start radius, you know, if you had of your sample, or end radius, or maybe you know the radius somewhere in between. Maybe you know I've got an enrichment of aluminium somewhere, and let's look up where that is, because there's a precipitate, and I know from an image what the radius is at that precipitate. Stuff like that. You know, you can use anything that works. Yeah. Okay, so with that, we can actually jump back into the reconstruction. And in this case, our effective detector area we can actually take from here. If you go into area, it will show you what the area. Why does it show it in integer? Okay, I have to go into that algorithm. It shouldn't show it as an integer. It should show it as a single precision floating point number, obviously. So okay, that goes onto the bug fixing list. But essentially, this the area variable that you get as an output from the detector Hull algorithm will show you what the area is independent of the hit index. So it will give you essentially what I've shown you earlier with, you know, if you have an underfilled detector and the detector then starts expanding, it will give you the effective detector area. But in this case, you know, we'll just know that it's 5. Our virtual detector is 5 millimeters in diameter. It has a detector efficiency in this case of about 0.37. Again, we would actually have to determine that properly. Our detector, our flight path, our virtual flight path is 5.5 millimeters. Again, I hope you remember what I've told you just earlier. And our image compression factor is 1.2, because essentially, it's a guess. Yeah, essentially we'll have to calibrate that against some known thing. Yeah. But the reason why in tendency in these reconstructions is a little bit lower than in regular reconstructions is just simply because we only see the image compression that is happening at the sample, and not the image compression that's happening because of the detector. That's not really that much of a thing in the reflectron systems. Because the distances are just much larger, so the area where the ion trajectories are influenced by the detector is just relatively small. And of course we get our post-dot ion volume, and so let's just run that section, and then we should have the entire setup for our reconstruction. We already have our radius calculated, so we'll just skip all of that, because otherwise we'll obviously override our nice radius estimate, and then we can go straight into our reconstruction. And one thing you can see here now is that we have a hull reconstructed and hull R, a hull reconstructed and a post reconstructed. And let me just visualize the results, and I hope in this case aluminium makes sense. Yeah. And so we've got our reconstruction here. So that the hull is actually outside of our data is actually more or less a MATLAB visualization artifact. It sometimes gets itself in a bit of a twist when you have patches, when you have sort of objects that represent points, and objects that represent areas. Yeah, and so that's a bit of a problem here. So is that representative or not? I don't know. Maybe it's a good reconstruction, maybe it's a bad reconstruction, but we should look into that later, if it's a good or if it's a bad reconstruction. But probably it's a little bit more squished than that. And so maybe the image compression is a little bit higher. Maybe it's 1.4. So I'll just rerun that section, rerun the reconstruction, and rerun the visualization, and we can see now it's a little bit more squished. Maybe it's even more than that. Just rerun the reconstruction. Obviously you can do all of that in a loop or in a script or whatever, and we'll make it very fast. And yeah, and this is just an assumption. With this data set, I don't know actually what the exact reconstruction, a good reconstruction would be. But we have a fairly nice reconstruction, and we have the dataset hull. Okay, so what can we do with the dataset hull, or what is that thing? Let me just open it in. Oh, Blender isn't installed. Oh, we need to install Blender on this computer. Bloody hell. The good thing about that is that actually all modern operating systems have viewers for 3D meshes, so we'll just save it out. And we have an exporter for that, so it's patch to obj, and what we want to save out is our detector hull, so that exists now here as a variable. Our hull reconstructed in this case, our reconstructed hull, and this is actually quite different. We can also recalculate the other hull. So let's recalculate that just so that we can see the difference between the two hulls. So this is now the whole hull using the alpha hull algorithm. Same hull, but just not as nice a mesh in comparison to our other hull. If we want to export it, we can just go patch to obj, and in this case we want to export the hull, the reconstructed hull. Oh no, patch. Sorry, I'm sometimes still living in my old code. Patch to obj, and I will just save it into the downloads folder. Oh, and I should give it a name. I don't remember what the run number of this thing was. So usually I would call it run number and hull. So it would be called R something 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 underscore hull. Hull reconstructed in this case. Hull reconstructed, and I will just save it. And if I then open my Explorer, in the downloads folder, we'll have the hull reconstructed, and Windows, the 3D viewer, we can just open it and we'll see the mesh appear here. We can obviously also visualize it in MATLAB, but the important thing was it's easy to export. By the way, you could just go onto a 3D printer and print it out on a 3D printer if you wanted to. So if you want to make nice 3D prints of your Atom Probe datasets, be my guest. So you can use the hull to do that. To just plot it in MATLAB again, so we already have it plotted in here. So the easiest way to do it is just to copy it out from here and create a new figure, and in this new figure just plot all of that and set the axis to equal scaling, and switch the 3D rotation on. And I'm not 100% sure about what you think, but I think that is a much nicer mesh. A much nicer mesh than the one we got from just doing it on the reconstruction. And the reason why we want this nice mesh is because tomorrow we're going to start modeling objects in the data sets. So we're going to start modeling grain boundaries, dislocations, and whatever. So we're going to start modeling objects, and for modeling of objects, we need to know where the boundary of the data set is. So we want to know where the boundary is, and this is the boundary of the data set. This is a nice boundary. This is it's a boundary. You can go and remesh that boundary with instant meshes and the like. We'll show you tomorrow. But this is always going to be better than this. And this is one of the reasons why we like to do our own reconstructions, because we get those nice meshes that outline the data set. So how did the whole mesh come about? So if I jump back into the algorithm, so you can see we have in the algorithm, oops, that was stupid. One of the inputs at the end is Hull Detector. Let's just open the algorithm to see what's happening there. So pause, reconstruct 3D geyser. So what's happening there is at the end we can pass objects into the reconstruction. And these are objects that have coordinates, any kind of coordinates in the detector space. And we have created the hull in the detector space, so we can throw it into a reconstruction, and there will be a co-reconstruction of those objects based on their coordinates, because we, for example, we can go in to the hull detector variable here. We've got the mantle, the top, and the bottom, and you can see there are this is just the outline, and you can see the individual outlines at certain detector hit in its index numbers and detector X and detector Y coordinates. And these are then co-reconstructed. You know, the faces, the faces are not changed, but only the vertices are changed. And they then get 3D reconstruction coordinates, co-reconstructed coordinates. And this gives us the ability to have those objects both in detector space and in reconstruction space. Just to give you a little bit of a hint about what we're going to do with all of that later is we're going to go and use all of that ability that we have to co-reconstruct to go the other way around as well. So what we're going to do is we're going to make bad reconstructions first. We're going to model something in that bad reconstruction, and then we're going to go round trip back into the detector coordinates and outline that object in the detector coordinates. So we're going to start today. For today, we're going to start with some simple objects. So we're going to throw some spheres in, we're going to throw some planes in, and so on and so forth. But this gives us the ability to go round trip with objects in our reconstruction. And this is really the key to optimizing your reconstruction, because you might know something about the shape of whatever thing you have in your reconstruction. And the reason why yesterday I said I'm so excited about the new Invisio atom probe is the hull that we have right now is unfortunately not the outline of our specimen. Our reconstruction could actually be aided a lot better if, you know, if we could take an image like this, or maybe a tomogram, and actually have the outline of that specimen, the 3D reconstruction we can get from the outline of that specimen being somewhere close to this outline here, because this will make a huge difference in how we can do reconstructions. Okay, with that, we're at the end of the second reconstruction session. And in the first afternoon session, we're going to have Andrew Breen from the University of Sydney. That's going to show us how to actually, you know, have a good qualified guess or have some idea of what those reconstruction parameters that we've used here so liberally, what they actually could realistically be, by looking at the crystal structure of crystals with known structure. So if you have aluminium, if you have tungsten, or if you have iron or whatever, you might just know that the interplanar spacing is a certain distance, and you can use that to calibrate your reconstruction. And then later on in the afternoon, what we're going to do is we're going to do our round trip reconstruction, and we're going to use some objects in our data to aid the reconstruction. What we're not going to be able to do today, or in this winter school, is to really go and take some external data and have some solvers that do the optimization work. But that's something for another day. But what we definitely can do is give you an idea of how to optimize your reconstruction based on the objects that you have in your reconstruction. Okay, so I'm pretty sure you've got plenty of questions that are floating around in your head, you can ask them now, or maybe they need to foster in your brain for a little while, and you can ask them later as well. So the most important question: how many of you managed to do a reconstruction? Okay, I see some green ticks that are not from Erlangen, so that's very good. Two green ticks is better than 0 green ticks. I hope it's more than 2 people. So one of the questions was, is the recording going to be uploaded to YouTube? Yes, it's going to be uploaded to YouTube. So today, obviously, we're not doing anything that's where we could have a problem with any copyright issues, because it's all our own code, and it's it's all freely available stuff. So we're going to upload the videos. Okay, then I will. Okay, then I will stop the recording.